Hey, what's up, guys? I hope everybody's doing okay. I know this will be a little strange, me teaching you via video, but we'll all get through it, and I think that you guys will be okay. And so I'm down here in my basement filming this thing, so overlook all the junk behind me. I wanted to go over some of the polarity and electronegativity stuff that was part of the assignment that I gave you guys on Monday. A few of you were reaching out to me and telling me that you were still having some issues, even after you'd watched the videos that I gave. And I thought that might be the case, so I wanted to go ahead and do a quick video to talk you guys through that. All right, so a couple of the charts that we're going to need to see and get a good idea about. You probably remember this guy, the electronegativity chart, and remember that each of the elements have a rating from 0 to 4, with fluorine, these guys up here on the top right corner, having the highest, and the lowest being down here on the bottom left corner. Okay, and another chart that we're going to introduce, and I'll come back to this, is this electronegativity chart. It talks about the different types of bonds. Okay, all right, so here we go. At any point, if I need to stop, you might see a little pause in the video where I've had to adjust screens or do whatever. So if something seems a little disjointed, just look over that and just keep following the video. Okay, so here we go. When we look at the covalent bonds, and we know that with covalent bonds, the big word is sharing. All of these elements are sharing the electrons between one another. But what we find is, even though, if I'm going to draw what happens when we have the Lewis structure for a hydrogen atom and a chloride atom. All right, so we know that that is the Lewis structure there, and you guys have drawn those like that. Okay. Now, while we look at that compound and we say, okay, everybody is technically, yes, they're happy. Hydrogen needs 2, it's got 2. Chlorine needs 8, and it's got its 8, and it's happy. When we look at the compound as a whole, and we focus in on the fact that over here on this chlorine side, notice how many electrons are surrounding chlorine. There's a total of 8, right? And there's only 2 over here with hydrogen. And remember, chlorine, going back to its electronegativity value, has an electronegativity value of 3, while hydrogen has 2.1. So what we notice is that because there is the vast majority of the electrons over here on chlorine and not so much with hydrogen, while we would consider the compound totally electrically neutral, we end up having this little partial negative charge that's over here on the chlorine, because, you know, just look at it, all of those electrons are grouped over there on that side of that compound. So it gives that end of that molecule this partial negative charge to this side. And hopefully that's intuitive and logical, because you've got so many negative particles over there, all those electrons. Well, that also, with all of the negative electrons being shifted over there, that just by nature gives a partial positive charge to this hydrogen side. And these little symbols are lowercase delta symbols, by the way. And we use them to indicate partial charges. So lowercase delta with a plus means that there's a partially positive charge on this side, and lowercase delta with a negative is partially negative on that side. And because we have these two items going on, we say that this particular molecule is a polar molecule. And that idea of something being polar just means it's got two ends. You think about a north pole or south pole, or a battery that has a positive pole and a negative pole, or a magnet even. All right. So some compounds we find that there is an unequal distribution of electrons. And that phrase in itself is what we use to sum up this definition of polarity. So polarity results from let me rephrase it like this. Let me just say that a difference in electronegativity values, let's spell that, negativity values, will lead to an unequal sharing of electrons, which leads to a polar molecule. Okay. So that is kind of, in a nutshell, this idea of polarity. Things are polar because the electrons are being shared unequally between two elements. And they're being shared unequally because those two elements have different electronegativity values. Think about it in terms of one is more attractive, so all of the electrons want to hang out with the more attractive element. Okay, so we also, another phrase that you might hear would be that polar molecules are caused by an unequal sharing of electrons. And sometimes that electronegativity value concept doesn't get thrown in with this polarity talk. But polarity is technically, it's grounded in the fact that those elements have different electronegativity values. But really, this is the big phrase here that people throw around most often, is the unequal sharing. Oh, that didn't work. That looks ugly. Let's change it to unequal sharing is caused. That's what causes the polar molecules to exist. Okay. Now, something else that happens is when we look at those electronegativity values, we find that I'm going to move this box around after I finish writing or typing. The character of a bond is technically dictated by the difference of electronegativity values of its elements. Okay, so here's what that means. And I know that we've talked about ionic bonds are formed when elements transfer electrons, and covalent bonds are when elements share electrons. Okay, I want to go back and I'm going to pull up this chart here, electronegativity chart. So look at the ionic bonds first here. So we've talked about those. Hopefully we're comfortable with those ionic bonds. And we know that one ionic bond is sodium chloride. Okay, and we know that we call it an ionic bond because it's between a metal and a nonmetal. Well, here is what really, really locks it in as an ionic bond. When we look at sodium and chlorine on this chart, we see that chlorine, there's that 3.0 for its electronegativity value, and here's sodium, 0.9. So sodium has a 0.9 and chlorine was the 3.0. Okay. So when we find the difference of those two values, and when I say difference, I literally mean subtract them. Just find the difference. 3 minus 0.9 gives us 2.1. Anytime we have a difference, an electronegativity difference, that's greater than 1.7, then ding, 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 that's when we have an ionic bond. Okay, and what we find is anytime that we have a metal and a non-metal, that difference is going to be greater than 1.7. So we have an ionic bond in that case. Okay, so we want to focus now on the covalent bonds. And we've got two types of covalent bonds. We've got covalent bonds that we call nonpolar and covalent bonds that we call polar. So polar covalent and nonpolar covalent. And the difference between the two comes down to wherever that electronegativity difference falls. Okay, so here's some examples of those. Let's say that we look at well, let's just take that the compound that we just did, hydrogen chloride. And remember, chlorine has its lone pairs around there. So chlorine had that 3.0 electronegativity value, while hydrogen has the 2.1. 2.1. All right, so when we find the difference between those, so 3.0 minus 2.1, obviously we've got a difference of 0.9. Well, that fits right here in this category. Anytime we have a difference between 0.3 and 1.7, so 0.9 obviously falls in that middle range there, we have a polar covalent bond. Okay? And we already established the fact that we did have a polar covalent bond when we said that, yeah, all of those electrons, they're hanging out over there with chlorine, and it gives it a partial negative. So we not only saw that it made sense, that it's a polar, but we also have that the electronegativity difference to back it up. Okay? Let me erase all this stuff. Alright, so let's take a look at another example of that. Let's say we've got a carbon and chloride bond. Carbon and chloride. So you guys know the drill, what this would look like as a Lewis structure here. So let's just look at it in terms of the two atoms, and we're just finding the values for those. So carbon and chlorine. So looking at my electronegativity chart, I've got carbon 2.5 and chlorine with a 3 right there. So 2.5 and 3. If I find the difference between those, that's a 0.5 difference, right? So that 0.5 difference would tell me that it's going to fall between 1.7 and 0.3. So I could classify this carbon chloride bond here as a polar covalent bond. Okay, polar covalent bond. I want to give you guys several examples of these. Okay, let's say we've got what if we have this set up here? You guys remember that compound O2? You know, we've got so many diatomic molecules that we talked about. So if we look at that molecule, what do we notice? Well, we've got the same electron setup going on over here as we do over here, right? So if we take a look at the electronegativity value of oxygen, 3.5, and if this is an O2 molecule, we've got 3.5 value for that oxygen, 3.5. Well, obviously the difference between those would be 0. So less than or equal to 0.3 means we've got a non-polar covalent bond. Okay, and hopefully that makes sense, that if you have a diatomic molecule, the difference there between them is going to be 0 because it's going to be the same value for both. So every diatomic molecule we have is a non-polar covalent bond. And here's the other thing. Think about, we already established the idea of sharing. Let's go back to that for a second. Polar molecules are caused by an unequal sharing of electrons. Well, if I have this oxygen, this O2, notice that all of those electrons are the same over on the left side as they are on the right side. So what do we have? We've got this equal sharing scenario going on here. So equal sharing is nonpolar. So, whereas unequal is polar. And we already said that. Okay, so it's all about how those electrons are distributed and the electronegativity value difference. Okay, so here's something else that we look at. We've got this idea of equal and unequal, and equal being nonpolar and unequal being polar. There's that. Okay. So we can actually take a look at the way that a Lewis structure appears and see if we think that the electrons are shared equally or unequally, and then get an idea of what we think the overall molecule's polarity is. So let's take a look at what are we going to do first. Let me see. Check my notes over here. Let's take a look at ammonia, NH3. When we draw NH3 like this, that's its Lewis structure. Now, here's where we want to start looking at the idea of symmetry and how symmetrical these Lewis structures are. So when I look at this Lewis structure for ammonia, NH3, if I want to look at symmetry in all aspects, not just over a certain axis. Now, if I just drew a line right down the middle of this guy right there, then it looks like I've got perfect symmetry, and I do. Everything on the left side is the same thing as on the right side. But if I were to draw the line this way and look at this as a top versus bottom scenario across this line, it's not going to be symmetrical, because on the bottom down here I've got this hydrogen atom, and on the top here I've got this lone pair. So this would be asymmetrical. Now, when I say that it's asymmetrical, think about what that means in terms of an unequal or equal sharing of electrons. If I've got a lone pair up here and a hydrogen down here, obviously this nitrogen has got these additional electrons up there. So there is an unequal sharing going on. So anytime we have something that is asymmetrical as a Lewis structure, that's an indication that there's an unequal sharing going on. And then guess what? That means that we have a polar molecule. So if it's asymmetrical, it's going to be polar. Another example of that, let's look at water. When we draw the Lewis structure for water, okay, there's the Lewis structure for water. And you might say, well, Stotts, if we go right down the middle, it is symmetrical left and right, but it's got to be symmetrical in all aspects. So if I were to try to bend it across that line, it's not going to be symmetrical. And check it out, oxygen has got those two lone pairs up there, and that creates this really dense, rich area of electronegativity. So here again, we've got a situation where the Lewis structure is asymmetrical, which means that there is unequal sharing of electrons going on, which means that molecule is polar. There's going to be a partial negative and a partial positive, which down here, partial positives are on these hydrogens, and a partial negative is up here on those lone pairs. All right. Let's check one out that is symmetrical. Okay. Take the compound methane. Okay. Notice here, you've got hydrogens on all four sides. You don't have any lone pairs. So you could bend that thing across that axis, you could bend it across that axis, you could bend it across that one, that way. You could keep bending it, and it's always going to be symmetrical because there is an equal sharing of all of the electrons. Look, those hydrogens are spread out on all four sides. And because of that, if there's an equal sharing, we would say that this is a non-polar molecule. So methane is non-polar. All right. Now one last example here of kind of a wrinkle. Carbon tetrachloride. Now, if you notice, this carbon tetrachloride is actually made up of 4 carbon chloride bonds. And we already established that a carbon chloride bond, we may have erased it, but we already established that a carbon chloride bond is actually polar. So just individually, each carbon chloride bond is polar because there's a electronegativity difference of greater than 0.3. But because they are placed in here and they are spread out evenly, and you see that those chlorines are spread out, and you can bend that thing across all these axes, even with 4 polar compounds in there, the overall CCl4 compound would be nonpolar because everything is spread out symmetrical and evenly. So just as a statement to sum that up, a molecule can be nonpolar even if it is made up of all polar molecules. Why? Because the electrons are shared equally throughout. This means it is symmetrical. Means it is symmetrical. Okay, so the last thing that I'll mention here is what happens when we mix these things together in terms of solubility. How do they mix together? Well, when we look at water and oil, we know the old saying that oil and water don't mix, and they don't, and that really has to do with the polarity thing that we're talking about. When we look at oil is going to be made up of your hydrocarbons, things like methane, things like anything that has carbons, hydrogens, and oxygens, and those things always are symmetrical and they share their electrons evenly. So that means anything that is oil based, think about like butter, no polar, non-polar. Have you ever had your hands in butter or grease and then you try to wash them off with just water? It just makes your hands slick. They're not mixing. Water is not going to wash away that oil because water is polar. We just looked at a water molecule. It was H2O. It's polar. So polar and non-polar don't mix. And there's a saying that like dissolves like. My pen will work. Like dissolves like. So if you've got oil or something on your hands or on, let's say, a pot, if you've been cooking and you need to get rid of that, you can't just use water. You're going to have to use some soap. And soap it's really it's a novel thing because soap will attach itself to the non-polar molecules. Soap kind of has these weird arrangements that have these fatty acid tails on there, and what that does is one end likes polar things and another end likes non-polar things. So soap will actually attach itself to the oil particles and allow the polar ends of the soap to be washed away by the water, thus taking all of the oil and grease and stuff with it. So that's why we use soap in the shower and why we use soap to scrub our dishes, because it's locking on to the non-polar molecules of the oil and the grease, and it's allowing the polar molecules of the water to wash those things away, where they wouldn't be able to just by water alone. All right, so that's when we're using things in the lab or in chemistry that we want to dissolve. If we're needing to break down something that's non-polar, we can't use a polar molecule to do that. We've got to have like dissolves like going on. We've got to have something that's non-polar. That would be the like dissolving something else that's non-polar, or vice versa. You've got to have something polar that's breaking down something polar. And water is typically really, really good to do that, because water is classified, sometimes it's referred to as the universal solvent, because even though water is a polar molecule, it still in some cases can interact with non-polar stuff, and that's why it works well for both instances, but it won't truly dissolve non-polar stuff. All right, so that's, in terms of solubility, that's the conversation with polar and non-polar. Like dissolves like, and the two will not mix. So I hope that this clarifies some of the things with the bonding, especially. Just in review, you can use these two charts, this chart here and your electronegativity value chart, to find the difference, the electronegativity difference between the two elements in a bond, and then classify them based off of that difference as polar covalent, non-polar covalent, and again, the ionic bonds are really easy to identify because they've got to have a metal. Okay. All right, so I hope this video helps. Just give me some feedback on it. I want to try to put this on YouTube, so if I do, I feel like I'm obligated to say, you hit subscribe down the bottom of the screen. If I was really cool, I could be able to like put some words here or something over here and point up over there. Yeah, I'm not into all that. So just give me some feedback and let me know if this is helpful, guys. And just keep me up on what you guys are doing. And I miss you guys, I really do. I'm not just saying that. I would rather be there in front of you than sitting here at my house behind my computer talking to you through this thing. But at any rate, you guys be safe, take care, and just keep me posted on stuff. All right, see you.